Okay, well, we've done as much proof as we have to do from the first chapter now, the first unit. So we're now moving on to, where are we? We're moving on to 1H, and this is counting principles. And then after 1H, we have the binomial theorem as well. So we're going to deal with factorials and what a factorial is and how to do some number work with factorials, how they cancel and how you can manipulate them. And then we're going to deal with some counting principle stuff. So in other words, how to make combinations of certain things or permutations of objects as well. These are quite nice questions. It's a little bit of a break from all of the algebra that we've been working on in this little section. So it's number work, and then it's how to make combinations and arrangements of things. Okay, so I'm going to skip the investigations in this case. I'm going to skip this one, and we'll just deal with factorial notation to start off with. And this question here, example 43. Now, there's a definition for factorial here. I might as well explain it separately, though. So, get with me. So, for example, if you wanted to do 5 factorial, choose to do 5 factorial here, then that would be the same as saying 5 times 4 times 3 and 2 times 1. And you could calculate that, I think it's 120. Okay, so that's 5 factorial. If you want to do 3 factorial, that's obviously going to be 3 times 2 times 1, and so on. Okay, so these are going to turn up, and some people might have seen these before in terms of this NCR or NR. So we're going to deal with this when we talk about combinations, but you also might know about that if you've already multiplied out things like A plus B to the power of N, so binomial expansions. If you know about that, then you will have seen these things turn up before, but you might know about this notation already. So 5 factorial is how you say this, so it's not 5 exclamation mark. 5 factorial is 5 times 4 times 3 times 2 times 1. So let's go back down to 1. Okay, right. So let's have a look at example 43. So it says find values for these expressions. Now, if we don't have a calculator to use, then you can do 7 factorial divided by 5 factorial is the same as 7 times 6 times 5 times 4, and so on, all the way down to 1. Okay, dot, dot, dot in the middle there. And then we've got divided by 5 times all the way down to 1. And then obviously the 5 is going to cancel, and all of the other stuff here is going to cancel as well. We're just going to be left with 4 times 6, sorry, not 4 times 6, 7 times 6, which is 42. Okay, so this one's 42, and for this one here, again, you can cancel the 3 factorial there. So you've got 5 factorial on the bottom. Now, obviously, 5 factorial includes 3 factorial, so you'll be left with the 5 and 4 on the bottom and 1 on the top, so you're getting 1 over 20. Okay, so pretty easy, this exercise to start off with. Okay, so when we're looking at this one, 8 factorial times 4 factorial, we can still look for the things which cancel. So again, we've got 10 times 9 and then times 8 factorial on the bottom. We have 8 factorial on the top times 4 factorial. This and this can cancel. And then we can think about what else we have cancel. Times by 10 times 9. And we can see there are 3 cancels with the 9. So 1 3 there and 3 3s on the bottom. A 2 can cancel with the 10. So we've got 1 2 there and 5 2s there. And you can see you're getting 4 times 1 times 1 times 1. That's this on the top. I mean, should be fairly obvious to you. And then you've got, that's meant to be a 5 times 3 on the bottom, so 4 15ths there. That's a 5. Okay. And likewise, you can do the same with D as well. You'll see that some things cancel. I mean, this is contained in here, and 5 factorial is contained in 6 factorial. So you're going to be left with, on the bottom, I think, this one, 10 and 9 and 8 and then I think as well, what else is going to be left? I think 6 is going to be left as well. Okay, let's just check that one. And yeah, that 6 is left on the bottom as well. If you look at the answer to D there, we're getting 1 over 4,320. This question, by the way, did say that you could use your calculator. So there's a calculator in the corner. And obviously you can find the factorial key on your calculator. Not sure where the shortcut is for that just at the moment, but it won't be hard to find. Okay, look how they've got brackets at the bottom. I mean, this is a little simple, I think, for you guys. So let's have a look at the next stuff. So now this is getting a bit more interesting because we're talking about factorials in terms of algebra. And so when it asks us to simplify this one here, we again should try and spot whether or not we can cancel the whole of something. Now, n factorial will be contained within n plus 1 factorial. So n plus 1 factorial, remember, is going to be equal to n plus 1 times n minus 1 times all the way down to 1. Okay, so in fact, n plus 1 factorial is really n plus 1 times n factorial. So if we replace this by this, we end up with n times by n plus 1 times by n factorial divided by n factorial. You can see that those two cancel, and you're just left with this. Okay, and let's have a look at the next one. This to me looks like we might need to do some factorization because we have two terms here, and we're going to perhaps need to cancel some of or all of this thing on the bottom with something on the top. So I think we're going to need to do some factorization, perhaps. Okay, so I'm looking for this for the first time here. So maybe we've got n factorial on the top minus, hang on a second, on the bottom I can see I've got n plus 1 times n factorial like before. And then we've got n minus 1 factorial there. I've not really done anything on the top there. Okay, so maybe let's just take it a little bit further here. Let's just say that n factorial is the same as n times n minus 1 factorial. So I kind of needed the same thing on the top. And I realized that n factorial contains this thing here, n minus 1 factorial. So it looks to me like I can cancel that now. So maybe I don't know with the bottom whether or not that was sensible or not. So actually I've got n plus 1 there, but then I can also see that this can be split up, n factorial into n and n minus 1 factorial, which is exactly what I did with the top. I'm just doing the same with this one here to give us this, the same as this gave us this. Okay, obviously these are equal. Now I can factorize out the top, making a bit of a meal out of this one, really. I've got n minus 1 there. So I've got n lots this thing, and I've got minus 1 lots of this thing. So I've got n minus 1 lots of this thing in total. Now underneath, I can see I've got this, which will cancel with this ultimately. So let's just write it the other way around. And then I've got n plus 1 times n. So those two things are going to cancel. And then I don't think I can factorize further there. So maybe I could multiply this thing out the bottom. Let's see what they do in the book. Oh, they've just left it in a factorized form there. Ooh, interestingly though, they've made a little mistake in the book, in this version, in this first version of the book. And you can see on the bottom they've got n plus 1 and it becomes n minus 1, which would obviously cancel, but it's not cancelling there because it should be n plus 1 on the bottom. Okay, now in newer versions of this book, that will have been ironed out. And as I always say, if you've got the code, if you bought the book, you can check this out using the online version. Okay, so where are we? So next bit, okay, so now it's starting to talk about permutations and combinations. Now, again, There's some good investigations which you can do here. So let's have a look at the pool party investigation, and there's plenty of descriptions as to how to do things here. And there's talk about coming up with a formula for permutations, which I'm going to discuss in a second. And then there's investigation 16B and C, and then there's combinations. Now, I'm going to go straight into example 45, but I'm going to do this in my own way here. So I'm going to do a little teaching just separately on this. Now, in terms of combinations, there are these two things. There's combinations and permutations of objects which you need to know about. So a classic way to build up a combinations question would be to say, first of all, A, B, C, D, E. How many words can you make out of A, B, C, D, and E? Okay, so different words. This being a nonsense word, but nonsense words being allowed, not necessarily English. How many words can you make from this? So, for example, E, D, C, B, A would be a valid example of a word. Okay, and then let's just extend this a bit and let's say, okay, well, what about if we have A, B, C, and D? So how many different words can you make there? So for example, if this was A1 and A2, and if I had A2 and A1 there, that would be the same word. So that wouldn't be allowed to be counted again. Okay, so if I just switch the A's around. So how many different words would you have in that case? And then finally, what about if you had A, and B, B? How many different words could you get in that case? Okay, now that's a really nice little investigation. Everyone can have a go at that one, and I really suggest that you do have a go at that for about 5 to 10 minutes. Play around with that. Even see how many combinations you can get. Don't feel the pressure of time. Just think, okay, well, how many of these can I write down? Now, you might actually want to write a list with this. This list will probably be pretty big. This list here is going to be really big. So maybe I'd start actually with this one, but you might get that pretty quickly as well. Okay, I will just let you pause this, and obviously I'm going to come up with solutions now. Okay, so number of different words in this case. Hopefully you got a choice in the first, second, third, fourth, and fifth places here. So you have 5 letters which you can put in the first place. Once you've used one of those 5 letters, you only have 4 left to place in your second place. And once you've used those 2, you now have 3 left over, and then 2 left over, and then you have no choice on the last one. So you've got 5 and 4 and 3 and 2 and 1. And I say and deliberately there because and in these situations, just like with probability, means times. So you're going to times those things together. Okay, so whatever combinations you had there with 4 of them, when you get to 5, you could put A on the front, you could put B on the front, you could put C on the front, you could put D on the front. So yeah, once you've got these sorted out, you could have different letters going on the front of each combination of these. I hope that makes some sense. Hopefully my first explanation made sense anyway. So this is giving 5 factorial. Okay, so when we look at the second one, now the clue I gave as I set this one up was to say A1 and A2 can be used interchangeably. So for example, A2 and A1 can be written this way around. So that means that whenever we have a combination, maybe we have A, B, C, D, and then A. It could be that we have this, but these 2 can be switched around, and that's the same combination. So hopefully you can see that in twice the combinations here, we have the same word being spelt out, because in half of the combinations you'll have A in one position, half of the combinations you'll have A in the other position, but spelling the same word. Okay, so in this case, we'll have still your 5 factorial, so your original number of words will be reduced by a factor of 2 because the A's can be swapped around. So they're interchangeable. They spell the same word. Okay, so for this one, you can say this is 5 factorial divided by 2. Okay, so that one should give us 60, and the number of combinations up here should be 120. So really much more work than you'd want to be doing on the page just by doing it longhand. So with the last one, which is really the most important example here, because this turns up in binomial expansion, binomial probabilities, the binomial theorem is turning up. So this is turning up a lot in mathematics. And so here you've still got your 5 factorial if they were all different. So in a way, if we call this A1 and A2 and B1, B2, B3, we've got 5 factorial ways of putting those around. But the A's could be either A1 first and A2 second, or A2 first and A1 second. So we'll need to divide by 2 there. But then we'll need to divide by the number of ways in which the B's could be around, because the B's fit into the slots wherever they fit. They always have an order. So you could have B1, B2, B3 somewhere in the word, but then you could have B1, B3, B2, or you could have B2, and you see pretty quickly there's 2 combinations starting with B2, and there's 2 combinations starting with B3. I won't write them all. So there's 6 combinations there, so we need to divide by 6 as well, because wherever the B's are, they will be in either this order, this order, this order, this order, this order, or this order, and each of them is going to spell the same word. Okay, so I guess what I mean is A, B, B is the same whether I have 1, 2, 3 there, or whether I have 1, 3, 2 in terms of the B's. So it doesn't matter, there's 6 different ways of writing the same thing. Now, in fact, you might be able to spot that divide by 2 and divide by 6 actually is the same as dividing by 2 factorial and dividing by 3 factorial. Because the number of ways of arranging these 3 things, B1, B2, and B3, is 3 factorial. That's 3 in the first position, 2 in the next position, 1 in the next position, 3, 2, 1 again. Okay, so in fact, we're dividing by 3 factorial. Right, let me just clear some of this out. So in the case where you've got A, B, 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 the number of distinct different words that you get is 5 factorial divided by 2 factorial divided by 3 factorial, that on the denominator as well, or times by 3 factorial. Okay, now since this is used a lot, there's a key for this on your calculator, and it will be on your normal calculator. You've got the Casio, let's just see what that one is. That's just above the divide key if you've got the old silver Casio, but you should be able to find that pretty quickly on your graphics calculator, whichever one you have as well. So seeing this is commonly used, you will notice that it is written as NCR. And when you get this on your display screen, it often turns up as NCR like this, but we normally write it down like this. Now there's another way in which we write it. We can also write it NCR. Oh, hang on. What is the N and what is the R? Well, the N you may be able to guess is 5 in this case. So this is 5. And we often call this, those combinations, we say choose. And that's going to become apparent in some of these questions as well. So we say 5 choose something. And in this case, it actually doesn't matter if we do 5 choose 2 or if we do 5 choose 3. They're both the same thing, right? Now the formula for this is we have NCR, or again, it can be like this. The general formula is when we have n factorial on the top divided by r factorial on the bottom, and then n minus r factorial on the denominator there as well. So in this case, if r was 2, then we put the 2 there, and 5 take away 2 would go there, giving us 3. But in this case, 3 would go there, and the 5 take away 3 would give us 2 there. Okay, so they're the same thing. Now, some people know this through making choices through a triangle as well. And so there's another way in which we could show this. Okay, so it's playing up a bit. There we go. So there's a way in which we could say, well, for our first choice, we've got the choice of either A or B. And for the next choice, we've got either A or B, and so on. You could do it like that. Yeah. Okay. I'm kind of thinking of trying to set this up as Pascal's triangle. In fact, I think that's a possible way of thinking about your combinations through the triangle. But this situation is analogous with that explanation. It's analogous with Pascal's triangle, which you probably know already. So, for example, Pascal's triangle is like this. Okay, 1, 3, 1, 1, 3, 3, 1, 1, 4, 6. Pen is running out a little bit there. Pen. So we've got 6, 4, and 1. So you can see what's happening here. We've got the 2 above add together to give the 1 underneath. Okay, so the 2 above add together to give the 1 underneath, and it starts off with 1 and 1 and 1 in a little triangle. So this is called Pascal's triangle, and the positions in here are really, this is, I'm going to write it in the notation like this. This is really 4, choose 1. This is 4, choose 2, and this is 4, choose 3, and this is 4, choose 4, and the one at the start is 4, choose 0. Okay, so you can also find, when we were looking for, say, 5, choose 2, you can also find that by doing making your Pascal's triangle, but obviously making Pascal's triangle takes a long time to do. So 5, 10, 5, and 1. So 5, choose 2, remember it's 5 factorial divided by 2 factorial, 3 factorial. Okay, in which case that gives us 120 divided by 2 is 60, divided by 3 gives us 10. So that's this position here. That's 5, choose 2. Okay, so it's this here is analogous with Pascal's triangle as well. I'm going to stop it with that because I'm going into a little bit too much detail there, I think. So let's have a little look at the types of questions which you can be given in these types of combinations, contextualized problems. So check these out. Do it through the questions. So first one says, in how many ways can the letters of the word candle be arranged? So we've basically got a choice of 6 letters in the first place, 5, 4, 3, 2, and 1 in the last place. So this is simply 6 factorial. Nothing hard there. For the next one, it says in how many ways can a group of 4 boys and 3 girls be rearranged? Okay, well, we've essentially got 7 students there, 7 boys and girls, and there's no conditions on those boys and girls, so they can be arranged in 7 factorial ways. Okay, they're all different boys and girls. Now, if they were identical, they had 0 personality, or they were identical twins or something like that. If you just didn't care and you were just saying, well, sort of what word does it spell out? That's a different problem. Okay, that would be, you've got 4 boys and you've got 3 girls, and you'd be saying, well, how many words can you spell with that? That's a different problem. But all of these people are distinct people. So it's still 7 factorial here. You can fit 7 people in the first place, 6 people in the next place, and so on. Okay, in the last question, then they say, in how many ways can a group of 4 boys and 3 girls be arranged if no girls are to be next to each other? Okay, that's a much more involved question, this one. So that's not what I was asking by saying the 4 boys and 3 girls can be rearranged to make, that 4 boys, 3 girls, and how many words have you got? It's not asking that. Now asking, we've got 4 boys and 3 girls. They need to be arranged, and no girls are to be next to each other. Okay, so first of all, let's just think about the 4 boys. We've got the 4 boys here, and we can put the 4 boys in 4 times 3 times 2 times 1 different ways. Okay, that's the ways in which they can sit. That's the number of combinations there. So that one's pretty straightforward. But now the girls they can go there, 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 but they don't have to go in those places because they can also go on the ends as well. Okay, now I definitely know that the 3 girls that I put in there, 1, 2, 3, are going to be in 6 different ways around, 3 times 2 times 1. But now there's my 4 boys ordered. Now I've ordered my 3 girls as well. And now I'm going to put those 3 girls into the 5 slots. So I've got 4 factorial boys, I've got 3 factorial girls, and I've got to choose 3 of the slots out of 5 to put the girls into. So I'm going to say for the other condition, because it's and, it's connected with times, I'm going to say I'm going to choose 3 of the slots out of the 5 for the girls to go into. Now, in a sense, that's like another problem. That's like saying I've got 5 slots and I just need to think about the pattern which they're going to fit. So, for example, we could put in girl, 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 no girl, no girl. Done that the other way around, right, with the X's. But okay, so I'm just dealing with this pattern here. I'm saying, well, okay, so that would be a valid pattern, but I don't know, this would maybe be a valid pattern as well. So there are how many different patterns? Well, that comes down to that question again of 5 factorial divided by 3 factorial, 2 factorial. Okay, so we're choosing 3 slots for the 5 girls to go into, or equally, you can think about it as choosing 2 slots to be empty. And that's the same as 5 choose 2, and that's the same as 10 as well, because of that symmetry in Pascal's triangle. Okay, let's just have a look at the answers there. So we have 720, 5,040, and then we have 4 factorial, 3 factorial, yes, and times by 5, choose 3. Okay, good. So that came up with 1,440. Okay, example 46. Here we go. How many 4-digit numbers can be made using the following digits only once? So the order matters here. And so for the first one, it's simply going to be 4 factorial. And you can calculate that as well. Obviously, you should come up with the actual number of ways. But you'll have 4 in the first space, 3 in the next space, 2 in the next space, and 1 in the next space. Okay, how many 4-digit numbers can be made of this? Okay, out of these 5 digits. Well, we've still got 4 spaces for them to go into. So we have a choice of 5 to go into this one, 4 to go into the next one, 3 to go into the next one, and 2 to go into the next one. Check that I've got that one right. Yeah, so actually it is the same as, it's just interesting because this is actually, they're talking about permutations here now. So actually that is the same as if I put another one on here, it would be times by 1 at the end. So in fact, there's the same combinations as if I was making 5-digit numbers instead. So again, we've got this times by 1 still gives us 5 factorial there. Now, why I question myself there just for a moment is because if they actually asked instead, changed the question and said, actually, we need to make a 3-digit number there, you'd have 5, 4 to go into the second space, 3 to go into the third space, and then we wouldn't be times it by 2 and 1 at the end because we'd only need a choice of 3. Now, this is in fact called a permutation. So in permutations, the order matters, and we're choosing 3 things in this question. It's an adaptive question. We're choosing 3 things to go into 3 spaces, and there is an order to those 3 things. Okay, so this would be what we call 5 pick 3. So this is permutations. And this is the same as doing 5 factorial divided by, and it's not divided by 3 factorial, it's divided by 2 factorial. So that's n factorial divided by n minus r factorial, r being the number of spaces which we have available. Okay, so these are called permutations, and often people say pick 3 from 5. So often people call this pick rather than permutations. And likewise, instead of combinations, people say let's choose 3 from 5. So people will often say choose or pick rather than combinations and permutations. Okay, so if we go on to the next one here, it says how many 4-digit numbers, let's remind ourselves of the question, how many 4-digit numbers can be made using each of the following digits only once? Okay, now we have an issue here because there's a 0 in there. And as starting with a 0 doesn't make for a 4-digit number. It makes for a 3-digit number because the 0 will just be dropped off the front. So we can't put 0 in the front. So here's our 4 spaces. So in the first space, we only have a choice of 3. But once we've taken out one of those 3, we then still have 3 to choose from in the second space, and then 2 to choose from in the penultimate space, and then 1 to choose from at the end. So this question is harder because it requires some creativity with the work that we've done so far here. So we've really got 3 times 3 factorial there. Okay, just check that one. Yeah, 3 times 3 factorial. And they've actually said they're 3 pick 3. Okay, so rather than doing 3 factorial, 3, they're saying 3 pick 3. Well, let's just check out. Remember, NPR is the same as n factorial divided by n minus r factorial. It's meant to be a bracket. So if we did 3 pick 3 there, we'd have 3 factorial over 3 minus 3 factorial. What's 0 factorial? 3 factorial divided by 0 factorial. Well, 0 factorial, for the purposes of mathematics, is equal to 1. Okay, a little bit like something to the power of 0 is equal to 1 as well. I'm not going to go into that now, but trust me on that one, 0 factorial is equal to 1. Okay. Right, 47, and then I think we've got 47. 3 questions here, and then we're into the exercise. Gosh, this is probably not going to take an hour, this one. Okay, so there are 8 boys and there are 5 girls who attend the senior mathematics club. Okay, so we've got 8 boys and we've got 5 girls here. And find out how many ways the teacher can choose a team of 6 students to represent the school if there are these conditions. Okay, so there's 6 students. And first of all, if there's no gender restrictions. So we need to choose. So it's going to be combinations. We need to choose from, not 11 this time, 5 plus 8 is 13. So we need to choose 6 from 13. Okay, so that's like saying, well, I suppose it's like saying, well, we can choose, let's have a little look at it like this. So 6 positions, we've got 13, 12, 11, 10, 9, and 8 to choose from. So that's NPR, but remember, it doesn't matter which order they're in. So we could have had any of those people, maybe this is person 13 and person 12 and so on. We could have had any of those people in 6 factorial ways around. That's kind of interesting, actually, because that means to say that NPR, so if we did 13P6, then we'd need to divide that by 6 factorial to get 13 choose 6. That's essentially what I've just done. Okay, now, I mean, it's obviously much easier just to say I choose 6 from 13, but it does work with picking there, but we're just going to divide by the 6 factorial different ways that those 6 people can be around. Now, let's just have a look at that again. So 13 factorial divided by 6 away from 13 gives us 7 factorial. So that's NPR. And then divide by 6 factorial. We can put that on the bottom, and that becomes NCR. Okay, right. Let's get rid of that. So for part B, it says the team is to be made up of 3 girls and 3 boys. Okay, so we need to choose out of the 8 boys, we need to choose 3. And out of the 5 girls, we need to choose 3 as well. Now, because I said and there, in mathematics, when I say 3 from 8 and 3 from 5, in these combinations, permutations, and also in probability, when I say and, I mean times. When I say or, I mean plus. In some courses, that's called the or rule and the and rule. Okay, so that's going to be your answer there. Let's just check that one out. Yeah, we've got 8 choose 3 and 5 choose 3, so that's good. And so for part C, that's B, that's done. And so for part C, it says at least 2 of each gender are included in the team. Right, okay, well, this one is more involved because at least 2 of each gender, well, you could have 2 boys and 4 girls. You could have 3 boys and 3 girls, or you could have 4 boys and 2 girls. Those are the different things that can happen. Now, notice I said or between each of those things. When I say or, I mean add. And I said and between these things. So when I said 2 boys and 4 girls, or, so it's going to be times and then it's going to be plus. Okay, so choose 2 boys out of 8. So 8 chosen, 2 chosen from 8, combined with, so and the 4 chosen from 5 girls, and so other combination, or, if you like. So we've got, what are we talking about? Saying I've got this combination, or I've got this combination. I've got this or this, so therefore I need to add. Okay, confusing myself there a little bit. So we've got 8 choose 3 times 5 choose 3, and the final combination is I need to choose 4 boys out of 8 times by 2 girls out of 5. And we're not overlapping in combinations there in teams because there's a different constitution for each of those teams. So they're comprised of 2 and 4, and these are clearly different because they're comprised of 3 and 3. So we're not overlapping in any of those cases. Now, I spotted that the book does this slightly differently first time around. So what I've done is the second version there. That's just what I've written out. It comes to 1,400 different ways. They've had a separate way of doing this. They've said, oh, in fact, if you cannot at least 2 of each gender included in the team, that would mean you cannot have a team with only 1 girl, or with no girls, or with only 1 boy. So they've gone through the combinations. They said, well, we know that there's 13 choose 6 in total different teams, but let's take away the number of teams which include no girls, no boys, or 1 girl, or 1 boy, essentially the same thing there. So they've done exactly the same thing there, except for they've taken away those combinations which are not allowed. So they've started with the maximum number of combinations and they've taken the ones away which are not allowed. I think the second one is more obvious there, but both ways are obviously valid. Okay, so for 1H, you have 12 questions there. And again, this is pretty dense. There's a lot of chat going on there. There's a lot of explanations. 12 questions. I would suggest that you do all of those 12 questions and make sure that you understand all of the questions beforehand as well. In terms of your notes, I would make sure that you have written down what NCR is, which is often written N choose R like that, and what NPR is. And I would remember the 2 formulas for those as well. What are the 2 formulas? You should be able to recite those ones pretty quickly in case you're working without a calculator. Okay, well, thank you for listening, and good luck with the exercise, and I'll see you later. Hi there, guys. Well, you can see it's getting a little darker in here. I wasn't particularly happy about my explanation for why Pascal's triangle was the same as NCR. So I just want to go back to that because not only wasn't I happy, I just completely bypassed it, to be honest. And I was scratching my head thinking, well, wonder how that really fits up with doing A, B, B, B. And I just figured if I write it down like this, I've got my Pascal's triangle here going 1, 1, 1, not very interesting, 1, 2, 1, 1, 3, 3, 1, and so on. You can see the numbers here represent Pascal's triangle. And then I figure as you go down per level, you're either choosing to go left or right. So I've just labeled them here, A to go left, B to go right. And if I wanted to say get to this position here, you can see that I need to do a certain amount of lefts and rights. So, if I put on my choices here, A and B and A and B, I'm talking about trying to get to this position here. So I've had to go, let's just follow one of these down. I've got A, B, A, B. Okay, so to get to that, I've done A, B, A, B. Okay, so, but I could have chosen a different version of that. I could have done A, B, B. Or I could have done a different version of that. I could have done B, A, B, A. Or, I mean, there's other ones, right? And the question is, how many are there? Could have done B, B, A, A. B right, A left. So it comes down to how many different ways are there through the diagram. And essentially, we can boil that down to the same type of question as the A's and B's. So, for example, in this case, we're really saying this is 4 factorial, but the A's could be in both ways around. Wouldn't matter which way the A's are around. It wouldn't matter which way around the B's are as well. So that gives us our 4 choose 2. So this is why I kept saying it's analogous. Okay, and likewise, if we want to get to the next level, if we wanted to do A, B, B, C, and want to know how many different ways there are of spelling this word, well, that's the same as, let's choose magenta, that's the same as doing A, B, 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 right? Will take us to this position here. So that's going to give us 10, the summation of this one and this one. There's going to be 10 different ways of rearranging A, B, B, B. By the way, there's also 10 ways getting to this spot because that's the same as doing A, B, B. It's the same. Okay, so hopefully that clears up why Pascal's triangle is the same as doing our NCR. Yeah, it's often in maths, it's a bit frustrating when someone just sort of glosses over something. So apologies for doing that. Okay, thanks for listening to that one. That was just a little extra there. And next time round, I think it's what have we got coming up? Coming up next, we've got binomial expansion, I think. Yeah, binomial expansion.